our review. So listen, the intention of this, are we going? Yeah, okay, so the intention of this is to be an intensive review of the course with eventually turning this into a workbook. So I will give a point on the final exam for every original mistake you find, even a typo in this. I think it's pretty clean, so, but especially mathematical ones. Okay, the quote. Anyone who recognize the quote? Besides James, who knows what it says. George Cantor was the guy who gave us modern set theory, who plagued us with modern set theory, and he said, with respect to mathematics, it's a lot easier to propose a problem than it is to solve it. And certainly that's true in this subject area. Okay, so the first page is just about the idea of algebra, reminding us of what we do with algebra both at the high school level and maybe linear algebra. And the first real idea that takes us back to the beginning of the course is when we think about solving problems in algebra, we have gotten over accustomed to the nice properties of rational numbers and real numbers. In particular, that they have fields. You know what a field is. Addition, multiplication, commutative, and associative. We have a distributive law that links the two. We have identities for both addition and multiplication. And every number has an additive inverse, and every number but zero has a multiplicative inverse. These are precisely the field properties that let us solve equations. But as we learned in class, not every number system has all those nice properties, and it changes what we can do when we solve equations. For example, there's no multiplicative inverses in integer arithmetic, except for 1 and minus 1. Matrix multiplication is not commutative. Complex numbers, the arithmetic's a little bit different, although it is a field. So the major aim of abstract algebra as a tool for understanding what you're already doing is it allows us to look at properties in their barest, most simplest context. And it's also a leapfrog if you go on to graduate work. The ideas of algebra are at the heart of every topic going forward. Algebraic geometry, algebraic number theory, algebraic topology. We even apply this stuff to statistics nowadays. So it's a beginning step into the real abstract. But here's an example that I think is worth. You can solve that linear equation by I, right? You just 13x is equal to minus 3, right? You can just look at it. But what are we really relying on to solve that equation? Well, what does equality really mean? This is really what you should, the way you should teach it. When two things are equal, I can substitute one for the other. So 8x plus 7 plus negative 7 must be the same thing as this plus negative 7 because those two things are equal. Adding the same thing to both sides is kind of, well, putting the cart before the horse, as we'll see as we go through this review. But this is really what equality lets you do, is substitute one thing for the other because they're equal. They're declared to be equal. And now I have associativity property of addition and cancellation laws of additive inverses give me 0, and the fact that 0 acts as the identity. I get all this nice stuff, right? And then I can add both 5x to both sides. Again, what I'm really doing is substituting equal values again. I have 8x plus 5x must be the same as this because 8x is equal to that, right? So substituting equal values. And then I use the distributive laws again, the associativity and then the distributive laws to pull the x out, right? That these are equal as a distributive law, and that those cancel is really has to be a distributive law because I don't know what x is, right? But I can factor out of 5 and minus 5, and that's certainly 0, and 0 times anything is 0 by the field property that multiplying by 0 by anything else gives me 0. You get the idea, right? If I really look at what I'm doing here, I need every single property of the real numbers in order to solve an equation. And so when I set up an equation with a different system, like integers only, or with matrices, I gotta be careful what I'm doing because I don't have all those properties, and I gotta know which ones are missing in order to be effective. And so, if I was restricted to the integers, for example, because I ended up with the final equation, 13x equals minus 3, that has no integer solution. Because the only solution is a fraction, and a fraction is not an integer. Okay, so just a reminder of why do we care about properties, really? We rely on these properties to do algebra, to solve problems. Okay, a little thought about proving things. This is not, I haven't covered this before, and I think it's very germane. What we're focused on mostly is proving things. In specific cases and in more general cases, but what is a proof? You've all had 300 or have had 300, so you must have some idea. I claim a mathematical proof is nothing but a game. Unless you're proving something that's never been proven before, the thing you're trying to prove is already known to be true. Right? So you can just say, well, yeah, this was proven by so-and-so in such year and be done. It's a game because you're only allowed to know certain things at any given point in time. And so in this game, what you're challenged to do is, given the set of things you're allowed to know at this point in time, you're allowed to believe, you select the premises that will lead you to the proof of the thing you want. And technically, right, you've seen this in 300, more formally, given the set of logical statements known as premises that we believe to be true, we show that this implies the thing we're trying to show by transforming P into S by the rules of logic, right? That's how 300 went. So here's a nice example of a basic proof. Prove that x squared is odd whenever x is odd. Well, the premise is going to be that x is odd, right? And that means I can write it this way because that's the form of every odd number. So x squared then must be by substitution of equal values. Right? If x looks like this, then x squared looks like that. But if I do the algebra, which is actually applying the distributive law twice, then I get that, from which I can factor a 2 out of this thing. So this is 2 times 2k squared plus 2k. Well, that's an integer. I have something that looks like 2 times an integer plus 1, and that's the form of an odd number. So x squared is odd. So notice that in addition to the premises, I had to assume the basic rules of algebra to complete this proof. So they're, in effect, part of the premises, part of the world I'm allowed to believe. Now this is something so basic that usually you say, well, square root of odd is odd, I know that. But, so that's why it's a game. Just, what am I allowed to know? Remembering the definitions, our proofs are in this course are related to groups, rings, and fields. Any set that has the same mathematical properties as R and Q, the ones we listed, is a field. The integers are a ring because, why? Not a field. Integers are a ring because don't have inverses, right? I need multiplicative inverses. More basic type of object is a group. I only have one operator, and the operator, remember, must be associative, must be an identity, every element must have an inverse. Z is a group with addition. The set of invertible 2x2 matrices with matrix multiplication is a group. In fact, it's the general linear group, right? So that's the idea. So now getting into the nuts and bolts. A review of sets, relations, and binary operators. One thing about mathematics, a set is an undefinable thing. There's no way to write a definition for a set. We have the same problem in mathematics that we do in language. Is how do you go to language from 0? What does dog mean? What does cry mean? We need other words to define them. Right? Well, set is kind of like that. You can't define it in terms of anything because it's such a basic object. So what we say is a set is anything that behaves like a set. Anything where we have a collection where we can decide membership precisely. And remember the symbol, x is an element of A, says x is in there. one of the members. We write X not A, indicates not there. The empty set is the special set containing no elements. Written with a Scandinavian capital O, basically. If A and B are two sets, the intersection designated this way is a set of elements that where it's true that X is in both sets. The union is the set of all elements that are contained in either, so we write this as, you get it, right? The complement of a set. Sets live within a universe of elements, which is often unstated, sometimes has to be, but in order to complement the set of all elements that aren't in A, we have to pick them from somewhere, so I need to specifically have a universe in order to do the complement. A set difference, A minus B, A backslash B, is always well defined, where essentially I treat A as my universe. That is, A minus B is all the elements that are in A, but not in B. And there's an example that you can look at. There's nothing really important. Here's a very important example. Q backslash the set containing only 0 is the set of all invertible rational numbers, the set of all units in Q, everything but 0. Okay, so that's basic set stuff. We'll use it heavily as we go forward. Okay, binary operator. What's a binary operator? The picture is really nice, drawn by one of my former students. You take a set, you take two elements in the set, you combine them some way, and you get an element back in the set. That's the picture of a binary operator. It's a map from S cross S to S. Right? S cross S is a set of ordered pairs. Because we don't assume that the binary operator is commutative, AB may get sent to a different place than BA. The addition operator looks like a map that takes pairs of integers and sends them to A plus B. That's a binary operator. So to be a binary operator, some basic points. It must map every possible ordered pair to some particular element of S. And to be a function, it can only map it one place. I can take one element and map it two places. Otherwise, I fail the vertical line test. So each element in the domain, S cross S, is mapped to just one element in the codomain, S. So if an operator obeys these properties, we say it's well defined. It sends everybody somewhere, but doesn't send anybody to more than one place. So some examples of useless, ill-defined operators: send AB to some integer larger than A plus B. That's ill-defined because there's lots of different possible answers for one particular value. 2, 3 can go to 7 or 8 or anything, right? Our regular operators, addition, multiplication, in integers, rationals, and reals, are all well defined. And we'll examine many other operators we already have as we go forward. But treating operators as functions, maps from, in this case, a map from Z cross Z to Z is awkward. So we have a shorthand notation where we just put up star or some kind of symbol between the things, but that means apply a function to those two elements and return an answer. That's the way, even at high school level, you might want to think about what plus is. It's a machine that takes in two integers and spits out an integer. It takes in two rationals, puts out a rational. It's a function. But this notation is called infix notation, and we routinely use it. For groups, we use star notation, where star could have represented anything at all. And so, if my map was the greatest common divisor map, it takes a pair of integers and gives me their greatest common divisor, my star might represent that thing. Right? So, this is an important idea introduced here. When I say A star B, it doesn't mean times. It could stand for who knows what. Right? It can stand for any kind of binary operator. That's well defined. That's keeping up. It's in the margin. Okay. it's sometimes helpful to view binary relations in terms of sets and relations. Remember what a relation is. A relation between two sets is any subset of the Cartesian product. Cartesian product is all ordered pairs. So every function is actually a relation where the ordered pair AB means that A gets sent to B. That's how we interpret a relation as a function. But because when I look at functions, I have to pass the vertical line test. If AB is in the relation and AC is in the relation, then B must equal C, otherwise I have an ill-defined function, right? So functions are a very special kind of relation. And further, for every A in my domain, there must be exactly one element of that form. A has to be sent somewhere, and that's what makes it well-defined. In the case of a binary operator, my elements in the relation look like this. I associate an ordered pair with an answer. So AB is, the elements that look like AB are the elements of the domain, and C is an element of the codomain. So viewed as a relation, it's still a subset of S cross S cross S. Yeah, so again, if the ordered pair, containing an ordered pair, if the ordered pair AB becomes C, that is an ordered pairs in relation, and ABD is in the relation, then C equals D, otherwise I have an ill-defined thing, right? And that's equivalent to saying that A star B is C, and this says A star B is D, because we treat the ordered pairs as input and output of a function. The most important kind of relation is equivalence relations that we consider when we do cosines. Okay, some properties. A binary operator defined in such a way is commutative if for every, this is a really big for every pair of elements I choose in the domain, AB, A star B gives me the same thing as B star A. Addition and multiplication are commutative in the integers, the rationals, and the reals, and in complex numbers. Matrix multiplication is not commutative. In general, AB doesn't give me the same answer as BA, even when the matrices are squared. A binary operator is associative if it doesn't matter, if the grouping doesn't matter. If A starred with the quantity B star C gives me the same answer as the quantity A star B starred with C, again, for every triplet. Right? So to prove either of these things, I have to show it in general, that it always works for every set of elements. And associativity can be hard to prove because of this, because you have to pick 3 arbitrary elements. Or if you have a small finite set, you have to show this for every triplet. If I have a set of size 8, that means 8 times 8 times 8 triplets have to be tested if I do it exhaustively. So either way, this can be a hard one to prove. Okay, here's a counterexample, a good basic high school education counterexample. Or even before, division of rational numbers is not associative. Division of integers is not associative. Because if I take 5 divided by the quantity 3 divided by 7, I get 35 over 3. Because dividing by 3 over 7 is the same as multiplying by 7 over 3. But if I associate differently, 5 divided by 3 divided by 7, I get 5 over 21. And here's another important general point about proving things. Only one counterexample is needed to show something is false. It has to work every time or it's not true. So for the case of division, we can find particular values for which associativity holds. For example, if 1 is the last value, it works, but that doesn't prove anything. Right? That's just, it happens to be a case that works. This is another very important point about proofs. If it says prove, one example doesn't work. not prove something is true by showing it works for a particular case. That's just a demonstration that it works, but not a proof. You have to show that it works in every case. Okay, another example of a non-associative operator on the reals, taking a pair of real numbers and sending to a real number, is exponentiation. If I do AB star, quantity AB star C, I get A to the B raised to the C power, which is A to the B times C, right? That's how exponentiation works that way. But if I put the parentheses on the other side, that's A times B to the C. Or A star, A raised to the B to the C power, which is that. And those are very, very different numbers. With A equals 2, 3, 4, A to the B to the C is, A to the B is 8, that's 8 to the 4th. But A to the B times C is 2 to the 81st, which is that number. Totally, totally different. So exponentiation is not associative. And associativity is a basic property. Without associativity, it's hard to do anything. How do we know the integers are associative? How do we know the integer addition is associative? Because we're told so. We don't have anywhere near the tools we need in this class to prove that integer addition is associative. It comes from how the integers are represented in sets. So we just assume it to be true in this class and many classes, but somebody had to prove that integer plus and integer times is associative. And it has been done. So we take those as given. Assuming that integer plus and times are associative, we can prove that rational arithmetic is associative, that rational plus, and it gives an example there. If you've never done this, it's a worthwhile exercise to show that P plus Q plus the quantity R over S plus that it works. Right? So we've shown it here that it's true for any three rational numbers. Basically, inheriting associativity from Z because rational addition is simply defined in terms of integer addition and multiplication, which we're assuming to be associative. Again, the game, right? Okay, first our term thing. Prove that the operator, that this operator, where I take two integers and produce A plus B minus the product, is associative. So that would be a good thing to pause the camera. Let's see where we can get with this. So